So, welcome everybody to this workshop, Lambda Calculus for people who can't be bothered to learn it. I was surprised to see on the schedule, I think there are at least 4 Lambda Calculus related workshops and presentations at this conference. That's a lot of Lambda Calculus. Did any of you go to the 6-hour one yesterday? Dana Scott, all day. Yeah, how was that?
Great.
I'm sure way over my head.
Way out of my head.
Yeah, this will not be a reprise of that at all. For people who can't be bothered to learn it part, that is because I'm not really going to teach you all of Lambda Calculus. It is actually quite a deep subject. There's a lot to it. There are many different Lambda calculi. I'm mostly going to be doing a little bit with the simply typed Lambda Calculus, which I think is something anybody can learn pretty quickly. And it can actually be a little bit fun. Also, though, we're going to be implementing it in America's favorite programming language, JavaScript. Now, this is not because I recommend JavaScript for functional programming or any practical purpose whatsoever. It's because I don't want to have to ask everybody to install Haskell or some other language. You all have JavaScript on your machines already. For those of you who don't know this, you may be slightly surprised by that fact. But I assume all of you know this. In your browsers, you have a console. It runs JavaScript. That's all you need. So easy for me. I'm also not going to be using very much of the JavaScript syntax, such as it is at all. Just anonymous functions, but we'll get to that. Again, just to reiterate, please stop me, ask questions. I don't generally like the Socratic method of teaching, but let's see if you can read my mind. What do you suppose is maybe the simplest, what you might think of as the dumbest possible question you might ask about Lambda Calculus? Does anyone want to take a guess? I'll never do this again.
What is it? Why?
Why what?
Why we need to buzzer before?
Huh?
Why we need to buzzer?
Well, I still.
Why do we need to bother?
Why do you need to bother?
What's the point?
That's a smart question. I'm looking for a dumb question.
What's a lambda?
That's it. Yeah, why is it called Lambda Calculus? Does anyone actually know why it's called Lambda Calculus? I know you know. No. I don't want you to. Yeah. Okay, good. I'm glad very few people know. This is an important point. It seems like a trivial point. This might be a little bit of mythology. Very quickly, I think it's kind of funny. All right, people are afraid of this. It's got a Greek letter. It's called calculus. If you're not a math person, I'm not a math person. It sounds scary, right? Forget the calculus part. You're going to count some things with it or something like that. So forget calculus. But Lambda, what is this Lambda thing? A little bit intimidating. This whole conference is about Lambdas, right? It's LambdaConf. Well, Alonzo Church, the person who discovered, invented Lambda Calculus, the story that I read in academic literature was that he actually wanted to use some notation from, I guess, the 18th century that looks something like this. Actually, like a little hat. If he had gotten his way, we'd be calling it hat calculus, I suppose. I know that sounds funny, but there actually is a hat calculus. Like, look it up on Wikipedia. It became a different thing. Back then, professors had secretaries. I'm actually a recovering English professor, and I never had a secretary. But typewriters couldn't do that, so his secretary ended up kind of doing that to represent it. You could do that with some slashes. This could all be a myth. I don't know. What does that look like? Yeah, capital Lambda, right? That's it. So they called it Lambda Calculus, and eventually went lowercase. I suppose it looks nicer. They use this for type systems now. That's it. So what is the point? I mean, okay, it's like a little bit of a factoid. Completely arbitrary, right? These are not things to be scared of. All of the names that are used in Lambda Calculus and much of functional programming, they're just arbitrary names. They're nothing to worry about. They sound a little bit intimidating. They certainly intimidated me. I may be more easily intimidated than all of you. But the point is, like, who cares? It doesn't even matter. These names are not important. Okay. I'm not going to do a lot of slides. In fact, originally, I wasn't going to do any, but I thought it's probably worthwhile to introduce the syntax of Lambda Calculus a little bit before going straight into JavaScript. I need to ease you into JavaScript because I know it's a little bit painful. And I should introduce myself. This is my name, Stephen Syrek, in case you're wondering about the pronunciation. I'm S.J. Syrek in all the places. And like I said, I'm a recovering English professor. And I just want to point out to you that if I can do this, you can do this. I have not been doing this for very long. I taught myself Lambda Calculus while I was learning Haskell not very long ago. I think I started a year and a half ago at the most. And I became very excited about it, enough that I was willing to do this right now. So I want to make that point not only because I want to be encouraging to all of you, but because there are two purposes to this talk in my mind. One is that maybe I can communicate something about Lambda calculus to you and why it's useful, why it's awesome, why it's the foundation of everything that this conference is about. But also, and for me more importantly, and for those of you who do have experience, and by the way, those of you who do have experience, feel free at any time to tell me when I'm wrong. I need that and I appreciate it. And also please help others around you. I want everyone to be able to come away from this presentation able to teach this material to somebody else. The only way the functional programming world is going to grow is if all of us become teachers. I know that maybe that sounds like an extreme statement, but we're a very small community. And for our own self-preservation, we need to expand, like expand or die. And the other reason I'm using JavaScript is precisely for this reason. You can go back to your places of work or to your friends if you can convince them to learn something called Lambda calculus. And everybody has a web browser, and you'll be able to open that up and show them some things without having them install a complicated programming language or some software they don't understand. Because like I said, anybody can learn this. So if you already feel competent with this material, then at the very least, you can help me develop this into a better presentation for teaching others, and then find a way to use this material to teach your colleagues, right? Because you may not get them to install Haskell, but you could, you can get them to open up a browser, and then you can just immediately start writing functions and show them how this stuff works. Okay, so that's enough of motivation, I think. Are there any questions at this point? I know that you wanted me to go over purposes and aims or something.
Perhaps just some specific examples of how perhaps Lambda has helped you better understand or otherwise change the way you do your code for something like Haskell or something else. Because we don't program in Lambda calculus. This is a mental exercise.
Don't you?
Pardon?
Don't you?
But it's very, so it's useful exercise for the ultimate, marathon or whatever.
I think it's, thank you for asking. I think it's really useful for developing an intuition for what functional programming is all about. Raise your hand if you're really not sure what functional programming is. Yeah, honest people. Yeah, exactly. Yeah. If you had to raise your hand if you think that you would be able to competently explain it to somebody else. That's the other kind of question. Yeah. Functional programming is programming with functions. Like, so helpful. I think actually this material will really show you what functional programming is all about. It's elementary particles, as it were. What has Lambda calculus itself taught me about programming? I think I only have a boring answer to that question. Haskell is a Lambda calculus. So, I made this joke, don't we program with Lambda calculus? Yes, if you're using a functional programming language, you're using Lambda calculus, you just may not know it. So at the very least, now you'll know it. And, I never really thought about how Lambda calculus specifically, I suppose I can look at a function and know that I'm doing eta reduction now, or that maybe I should do eta reduction. I guess there are places in which it helps me with refactoring or conceptualizing. I'm not going to be talking specifically about that, I don't think. I guess I would maybe be able to talk about how Lambda calculus gives us for free all of these features that we hear about when we talk about FP, right? Like referential transparency, immutability, currying. What are some other good ones? I don't know, fixed point recursion. Well, anyway, that stuff all just sort of falls out for free from Lambda calculus. Anyway, let's get to it. This is the whole language, right? World's smallest programming language. Maybe actually the first programming language invented. 1933. Anyone know the date? 1933. You can look it up on Wikipedia. Alonzo Church, Lambda calculus. Before there were computers, right? They got it right the first time. This is the whole language right here. Concentrating first on the first line, you have anything in Lambda calculus is an expression, and there are three kinds of expressions: names, functions, and applications, and that's it. A function can be a name, so the lambda name dot. I'm going to explain all this a little bit in more detail. Lambda name dot expression, and an application is just two expressions next to each other. So you can see how this is a bit of a recursively defined language. The lambda in the second line, that's the famous lambda that everybody wears. Does anyone have a lambda on their T-shirt right now? I'd be surprised actually if nobody did. You're probably all wearing one on your lanyard thing. It's just an abstraction operator. If you're a programmer, you're used to abstraction, even if you don't know functional programming. All that is saying is create an abstraction called name and bind to that this expression, whatever the expression is. And then function application is two expressions next to each other. So if you're used to Haskell syntax, the reason why we don't have parentheses in Haskell is because function application is kind of the only operation we have. So we keep it simple. It's just two expressions next to each other. I'm so happy to have a blackboard. I don't do slides. I'm so more used to blackboards personally. God, this is like very fat chalk. I'll be showing some expressions soon, but I just want to make this point. So you can have something like lambda x.x. We actually call this the identity function. And this part here, we can call the head. This part is the body. This is an expression. Obviously, x has no meaning. This is an abstract syntax. Whatever you have here, whatever the expression is, it's just some stuff that we're going to compute under this thing, lambda x. You've heard anonymous function. It just doesn't, I mean, I don't like anonymous function. It doesn't have a name. It doesn't matter. This operator creates an abstraction out of this expression. And the x just means that like this x and this x are the same. If you're used to functions that look something like this, right? It's just text substitution, really. I mean, really, it's just text substitution. This was invented before there were computers. And in fact, with the Lambda calculus, as simple as it is, you can model any computation whatsoever. That's what's really neat about it. Maybe that's a good answer to your question. You can compute anything that can be computed with this. It doesn't seem like you should be able to. I hope I'll prove that. I mean, there are things you can't compute, and there are things you can, and that's just sort of a property of nature. And this sort of captures that in the simplest possible way. So there's an expression, x. It's just something x. Lambda x.x, I just showed you that. This is a function. Head dot body. Lambda x dot lambda y dot xy. This is another expression, and you can think of this as a function with two arguments, x and y. And lambda x dot x in parentheses applied to y. And this is not terribly different than if you had simply x, y. This is also function application. This lambda x dot x, y is also function application. And by function application, again, I mean text substitution. It's probably worth not thinking too much about functions as procedures or what you're used to in imperative programming languages. We have lambda x, little lambda x dot x, y. And function application means we're doing text substitution. So the y substitutes for this x in the expression. So this goes away, and we're just left with y, right? Y goes into x, turns into y. This is also a function application, and it's not more complicated. They get longer and more. They look trickier, but ultimately the rules are the same. Lambda x dot x, lambda y. Anybody want to guess what this turns into? Yeah, right, because this whole thing goes into here and is substituted for this x, so we're just left with that. This is one of the operations, actually, beta reduction. So again, anybody want to guess? I get another guess for the audience. When we say alpha substitution or alpha conversion, where does the alpha come from? Why alpha? What's the dumbest possible answer? Yeah, that's it. You have to call it something. Mm-hmm.
Actually, before we can go on, can you, on the last slide, can you write the third and the fifth one using the alphabet notation?
Oh God, I can try. The third one?
Yeah.
Okay. Lambda x, lambda y, xy. Lambda x. Write that using like f. Okay. Well, does somebody else want to try? I mean, I could do it, but maybe someone else should do it. Don't do it in JavaScript. I mean, I suppose you could have f of x, y, and then you could apply that to 1 and then 2. I mean, these don't do anything, right? We don't know what x and y mean. Like, it's just a function. It's just a pure, oh, there's the other one, purity, right? Functional purity. It's just a pure function. It has the same input. For any given input, it has the same output, right? Like anytime, whatever x you give it is always x. It's always the same, right? It's like a mapping between sets. Is that helpful?
I have no idea what this looks like. I was reading the whole but I'm trying to figure out what this looks like now.
When we get to the JavaScript, wow, I never thought I would say this sentence. When we get to JavaScript, it'll make more sense. Okay, so here's alpha substitution. Again, the variable names they don't mean anything. They're you can use any variable that you want. And yeah, I'm being very funny by using poop emoji, but the point is these are all the same. Okay, I'm going to use this triple equals a lot because this is not equality per se. Like, these are all actually identical. Lambda a.a, lambda z.z, poop, whatever. They're all the same. All of these represent the exact same things. You can substitute them one for the other. And you sometimes need to do that in complicated lambda reductions, which we are not going to do, right? Because you don't want to learn lambda calculus. That's why you came here. When we get to the JavaScript. Sorry, yeah? Legibility. But no.
You're like separating the arguments from the expression. That's what the period is. It's not like a.
Yeah. A is the argument. Lambda a, that a is the argument, and the a after the dot is the expression. Yeah. Otherwise, it doesn't matter. It's just notation, right? This is not a programming language. Oh, I'm sorry. This is a programming language. This is not something you can run on a computer. Here's a slightly more complicated. That was alpha substitution. This is beta reduction. I kind of did a few already, so I hope this makes sense. You have lambda x, lambda y, x, y, applied to p and q. So first you apply the p, the x goes away. Now you have lambda y dot py. Then you apply the q, the lambda y goes away, and you end up with pq. Does that make sense? I'm actually, it worries me sometimes that this stuff doesn't actually make intuitive sense. So if it doesn't make sense, I will explain it in more detail. Like, again, I thought I was going to get 10 people, and I'd be, does it make sense to you? I could go like, but I know. Well, we're going to get there. This is just supposed to be a warm up. I actually don't want this to take that long. This is kind of neat. Lambda x dot xx applied to lambda x dot xx, and when we reduce that, we get the same thing, right? Because if you plug this into this expression, this x goes away, and you actually substitute this for both of these x's, right? And then you get the same thing again. Recursion. You can do recursion with pencil and paper. I thought that was pretty neat when I first learned it. And finally, ADA conversion. This is mostly for your information. It's not going to be terribly important for the talk today, except ADA conversion will come up in one very important place later. What I'm saying here is that maybe this is the math part that will help. I don't know. So, I can't really make it simpler than it is. Lambda x dot f of x is just the same thing as f, right? The x is superfluous. It's the same thing as a function f, right? So if you have a function f applied to an x, you can put that into a lambda abstraction. That is the same thing as f itself.
One thing that's useful to kind of catch there is that the first expression, you have your x is bound. It's no longer a free variable. So that's kind of useful if you think about, like, am I handing off a function? Or am I handing off...
Which one?
That last
Lambda x dot f of x.
Yeah, and the first one you got your x, which is a bound variable.
Yeah.
Right?
Yeah.
And the other one is not.
Right.
So in one sense, in terms of closure, you're essentially
That's a good point.
handing off a function as opposed to handing off a value.
Okay, that's a good point. I wasn't going to talk about free variables. So yeah, the f is not bound in this expression. So if I were actually teaching you lambda calculus, which I'm not supposed to be doing, I would say that the f is a free variable. So it's f in some global state. We don't like global state in functional programming. But still, yeah, it represents some like global binding f. but these two things just happen to be identical in meaning. So that the f is the same in this case. That's a good point. Okay, so let's get right into combinators, right? Another scary word. I like to think of a combinator as, well, a combinator is a function with no free variables. I guess we can say that. It's a function you can combine with other functions to do some very neat things. So we've already seen this one, lambda x dot x. We call this the identity function because whatever we give it, we get it back again. And this will prove to be useful and important in many places in functional programming. This is also, I guess you could say, the universal fixed point combinator. That sounds scary too. A fixed point function is, the fixed point of a function is the value that when you give it to a function, you get the same value back. There are many examples of this in math. I'm not going to go over them, but I hope you can see that for this function, lambda x dot x, whatever you give it, you get back. So that's what I mean by universal fixed point combinator. Fixed point combinators will also come up again later in a much sexier way. This is what the identity function looks like in Haskell, my favorite programming language, and yours too, I assume. It's not easy to type a lambda on your computer, so we have a slash there instead, but that represents a lambda essentially. This is what we're going to use in JavaScript, assuming that your browsers are all up to date and you have fat arrow functions. Same thing, very simple, right? This is the basic building block that we're going to use. Anybody know what this is? Yeah, Python. Anyway, what about that? Yeah, this is good for me to gauge the room. Who knows what? What about this weird looking one?
Ruby again?
Not Ruby.
Java.
No? Yeah, it's Rust. Can you do this in Java? I don't actually know Java. I'm proud of the fact. Yeah, okay. I learned to program. I've been programming like as a hobby my whole life. I lost interest in the 90s, which is when Java started becoming popular, and then I got back into it not very long ago. I feel like my great pride in life is I missed the Java period. I hope. All right. I'm sorry if I'm moving too quickly. I do want to get to Java. I do want to get to JavaScript. I can't believe I'm saying this stuff. So now we have a very simple notation for creating computations, but it's a little bit clumsy. So we need to actually start creating some primitive values. So we can create true. And again, this is not a binding in the sense of like a variable binding. These two things are completely equivalent. They are substitutable one for another wherever you see them. So we're just going to say lambda x dot lambda y dot x means true. So this is simply a function that takes two values, an x and a y, and it returns the first one. And we're just going to say that that's true. You know, you could do it a different way if you want, but we're going to use that as our convention, right? We're just going to encode true as this function. And we're going to encode false as the opposite. It's a function that takes two values and returns the second value. That's it. This is not like some standard of lambda calculus. This is totally a convention. It's the convention that is typically used, so I'm using it, but we're just making it up. Did I see a hand somewhere?
Yeah, sorry, I was just going to interject. If somebody's trying to use Node and you're using new language features, it might not work. So you can use Babel. I'm going to put that in the chat.
Yeah, okay. Yeah. I think actually that Babel inspired me to do this at some point. I was very frustrated with trying to learn lambda calculus. I started messing around with it in JavaScript because it was there. And then eventually one thing led to another. Here we are. Okay, we can make more complicated functions, logic functions like and. So I hope that if you look at this and you're a programmer, this makes sense. If you have two values, you can determine whether or not they are both true by you look at the first one. Is it true? Okay, if it's true, you compare it to the second one. And then so let me be clearer here. So we have two functions, true and false, right? True returns the first value, false returns the second value. So if A is a Boolean value, true or false, if it's true, it's going to return whatever B is. And if it's false, it returns false right away because it's an and, right? If B is a true, then it's true. If B is false, then the whole thing is false. Does that make sense? That's why that looks like that. Yeah.
Well,
I can do it on the board too. But
yeah, the thing is,
I hate chalk.
The trouble of lambda calculus is the notation,
Yeah.
right? From my understanding, I see that basically when you see lambda x, it means the function f. And in the first situation, it takes like two variables, like f of x comma y.
Mm-hmm.
And in this case, it returns x.
Mm-hmm.
Then in the second question, it takes f of x, y, then it returns y.
Yeah.
In the third case, it takes two arguments and it returns an and
Yeah.
of both. That's basically it.
Yeah, same thing.
All right.
Yeah, it really isn't more complicated than that.
Because the notation is just what is causing the confusion.
I mean, here's the ultimate cop-out. I didn't invent this notation. But, you know, it provides us a universal language with which to speak about functions and function application. Right? So when I said this is what functional programming is all about, is literally everything is a function, right? You've heard everything is a function. What does that really mean? Functions are values. We're just saying lambda x dot lambda y dot x is true, right? It is the value true. We're simply encoding truth as that function. And then we can do stuff with that function to build up more complicated expressions. So there's an and, there's an or. We can do not. And you know, now we have Booleans, right? We're getting close to being able to do actual logic, and it's all functions, right? I mean, I don't know how you feel about this inside your own heads. This was mind-blowing for me when I first learned about it. So reducing expressions, we can take an and and a true and a false, and if we put the lambdas back in, it looks like that. Already, it's starting to be headache-inducing. I know. The point is, and true false is identical to this expression. It's easier for us as people to deal with and true false than with all of this lambda stuff, but you can actually still work this out on paper. You can perform these reduction steps that I showed you, and ultimately there's the first step of the reduction, another step of the reduction, another step, another step. By the way, the slides are all on GitHub, so you can play with this later if you like. Eventually, all of this reduces down to this function, right? These are the reduction steps. If you are plugging things in and replacing your bound values in the expressions at each step of the way, finally you get to lambda x dot lambda y, which we already know is false. That's how it works. That's how you do a computation, anyway, in lambda calculus. A very simple one. Mm-hmm. I can, but why do you want me to? I would just be writing. I mean, look, I'm going to be honest with you. I hate touching chalk, and I am trying to avoid it. I will do it if necessary, but I would just be writing that again. I mean, you want me to like go through the whole thing?
No, that's fine.
Yeah, I mean, I will do it later, pen and paper, but it'll take too long.
Okay.
I only have 2 hours.
I think you were just saying the end in the last slide, maybe just talk through it, even if you don't write it, it's confusing. Is it arbitrary, like true and false? Or
Yes.
Okay.
Yeah. Yeah, I'm just saying yeah. I'm just going to say that's true and that's false. Just like truth and false in real life are arbitrary. Yeah, you came for the deep stuff today. I know you want to look for some meaning, but like I showed you that first slide with the that's it. That's the whole language. Those 3 things are the whole language. I have to build the entire system of computation out of that, out of just functions. So if I want to do Boolean operations, I need some notion of truth and false, right? If I want to do comparisons, so I just have to invent them, right? I have to invent them in a way that they'll work, and this happens to work. It seems like a bit of magic, and I guess it is.
You're saying they're arbitrary, but they're not arbitrary in comparison to each other. These are built up in such a way that
The system is logically, the system is logically consistent. Yeah. It actually has. It developed out of the study of logic, in fact, formal logic, not stuff I know a whole lot about. But yeah, they're not like random. They're sort of encodings that were decided upon as part of a system that is internally coherent. Wait till we get to numbers. Okay. So now that we have some Booleans, we can actually create useful functions. So here's a function that determines whether or not a value is 0. I've rearranged this presentation since the last time I did some piece of it, so we don't have numbers yet. Bear with me. So let's say that x is a number. This function will tell you whether or not that number is 0. This is a maybe easier way to look at it, right? Is 0n, and so so is 0n is going to return a true or a false, right? And if it returns true, then so we're applying. I think I need to maybe explain this a little bit better. So this is 0n is going to reduce down to a true or a false. We know that true returns the first value that it's given, right? So it's going to return true. If it's not 0, it will return false, right? Because false returns the second value. That's it. We're applying true and false to this function is 0n. Yeah? Oh, you're gonna love it. And I think it's on the next slide. Yeah. I wanted to do predicates after Booleans, so the numbers are slightly out of order. So bear with me. Okay, so now we can have branching in our Lambda calculus, right? We can say an if statement is simply a function that is a predicate, right? A predicate is a function that returns true or false. And then we apply to that two values, x and y. And if that predicate p is true, it will return the first value. If it's false, it returns the second value. Yeah?
What's the definition of 0? You're saying is 0 true or false? What is the definition of 0?
We're going to get to that.
Okay.
Yeah, like very soon, like imminently. So that kind of would look like that, right? If n is 0, then you would do the value in that then branch. Otherwise, the else, right? And actually, we can factor out the p, the x, and the y, and we can just say that if is the identity function. It's the same thing, really, because we're just dealing with predicates. Whoops. Right, that's, if you want to write it as like a little law for yourself, right? P, expression 1, expression 2, if p is true, then E1, else E2. Okay, everyone wants to do numbers, and you know what? I don't blame you, because how the heck do you do numbers with only functions? This is really where the whole idea of functions as values, I think, is going to make sense, and I hope I'm going to drive this home for you. Speaking of arbitrary, we're going to call 0 a function that takes an x and returns an x and does nothing to it, right? Lambda f dot lambda x dot x. We're just going to say that's 0. Right? That's a 0, but I mean, it's just an encoding, right? Ultimately, you can encode it in binary. That's another way of encoding it. It's again a convention, right? This symbol represents some idea of 0. It's not like we are so used to using it. We think, well, that's 0, right? And that's 5. But it's just a symbol. There's 1. Lambda f dot lambda x dot f of x. You're going to see a pattern very soon. So now we're taking a function and a value, and we're applying the function to the value one time. There's 2. There's 3. You can probably guess what 4 looks like, and possibly 5,000 at this point. Because what is a number? If you're doing something with a number in computation, you may just be storing a value, but very likely you're probably going to be performing some operation that number of times, right? For any number n, you're going to do something n times. That's all that this is doing. Some number x, if you want to like do something with the value 3, then you apply with a function. You apply that function to the value 3 times. 4, 5. It gets ridiculous. And by the way, again, this is not variable binding. These are identical. I'm just using this as a convenient symbol. You could use poop emoji here too if you want. I want you to be able to read this. So all of this stuff, I don't want to type that ever again, especially when they start to get really big. So I just attach convenient names to them for my own benefit. Now enumeration, we can actually work with these numbers and get somewhere with them. There's a function that will tell you what the next value is for a given value n. This one's more complicated. I don't want to divert too much into these things. So you'll have to. So again, I'm not meant to be teaching you Lambda calculus. This is taking too long. I just want to show you that you can do this kind of stuff, and that this is the basis of functional programming, right? These are functional combinators where all values are functions, and you can actually do computation with just functions. Pred is complicated, and it actually was kind of a discovery at the time because they didn't know how to do it. And it will tell you the number. So suc of 2 is 1, and suc of 2 is 3, and pred of 2 is 1. That's what those are for. There's the reduction. You can write it out on paper if you don't believe me. It totally works. The number after 1 is definitely 2, and the number before 1 is definitely 0. They work. I tested these. Now we can do some complicated arithmetic. There's add, and at this point I'm going to start going a little faster because the actual encodings don't particularly matter. The fact that we can do them is what matters. Different ways of doing add. They both will give you the same result. Subtract, multiplication, exponent, which is delightfully simple. Totally makes sense, though, that you're applying a function that gets applied a number of times to another function that gets applied a number of times. Now you have an exponent, right? Here's a reduction. If you add 1 and 2 together using functions, you get 3. You get a functional encoding of 3, right? Now, if you're doing functional programming, you're not going to write all this Lambda calculus garbage. But this is the underlying substrate, you might say, of the functional computation. And it ultimately gives you the correct answer that you want. This is just a very simple sort of program. Subtraction is a little bit more tedious. I mean, tedious for me. I'm so terrified of being wrong. I sat down and wrote these out on paper. I encourage you to do that just to get an intuition for it. Multiplication and exponentiation. Look at that 8. I think it's crazy. All the parentheses. All right, now this is the hot stuff. Raise your hand if you've heard of Y Combinator. Like the company, right? Yeah. I hope you all end up. Do I hope that you all? No. Anyway, raise your hand if you've seen the Y Combinator. This Y Combinator. Okay. So I don't know if you are aware of this, but the company Y Combinator, the name is based on this function. This is how you perform recursion in the the untyped Lambda calculus. I referred earlier to fixed point combinators, and this is a fixed point combinator for functions. Any function, this will, for any function that you give fix, it will return that function again, and that is how you perform recursion. For example, everyone's favorite example, factorial. Here's a function that will perform a factorial, but we need to do recursion to perform factorial, right? So we'll say factorial is going to be a function that is the fixed point of this function f. We're going to pass f to our fixed point I didn't call it y because I want to be clear. The fixed point combinator is a function that when you give it a function, it will return that function again. It actually kind of embeds the function into the expression in a way that you're going to see in a minute. Honestly, the details aren't important because you're not here to learn lambda calculus, honestly. But I want you to get a sense for it, an intuition, right? So we're going to take the function f and we're going to pass it to the fixed point combinator. And it looks like that. That's what we get in the first reduction step. And you can see the f is now embedded into the recursion. And that's how we can perform a factorial operation, right? There it is again. And it looks like that. And it will keep doing that until we're done, until we reach our base case. The base case, right? The is 0 end part. Without the base case, then it doesn't stop. That's a lot of writing. I'm going to walk you through the recursion now, step by step. I don't expect you to. This is mostly for entertainment. This is what it looks like when you write this out, right? So we're going to calculate now the factorial of 2, step by step. And we're doing beta reduction right now. It's just text substitution. We're putting values into functions. I'm actually cheating a little bit because I'm not expanding all of the lambda expressions. Because I know that whether or not a number is 0, so I'm just doing this in my own head. But this is an accurate representation of the reduction, right? At each step. It's almost legible, right? Even if you don't know lambda calculus, you know a little bit of programming maybe, you can see how this would work to calculate a factorial. And I end up with that, and I know that 2 times 1 is 2. I can do anything now, right? I have numbers, I have recursion, I have branching. I can calculate anything. You wouldn't want to calculate anything in lambda calculus like this, but you could, in principle, you could.
So just driving home the point that the first step of get the substitution. So you're building everything. So the first step is that substitution to build this whole thing out, and then the next step is evaluation, kind of shrink it all down.
Well, I mean, not exactly. Okay, maybe the point is abstraction, right? Because I don't want to write lambda expressions, but I want to be able to trust that this stuff is going to work without worrying about the notation. When you get to a real programming language, then obviously you're not worrying about this. This is sort of how functional programming works at some very primitive level. You might think of it that way. Like when you write programs, you're not writing stuff like this. But if you're working with pure functions, right, you don't worry about state, then you know that when I write fact, I'm really writing like fact f or whatever. I'm writing all of that lambda stuff, and it will work the same every single time. I would rather work with named functions because they're easier for me and named values than with like long lambda expressions. Yeah.
Doesn't this have like very concrete implications in terms of like currying and like delivering expressions? Like that's why it's under the hood. It's why all that is possible.
Yes.
So,
Yes. Yeah. I wasn't going to say it yet, but yeah. Look, you get currying for free. It's right there because you're applying each argument one at a time. I mean, if you're familiar with currying, that's what it is. Instead of applying all your arguments at once, you can do them one at a time. and you take a function, you apply an argument, now you have a new function with that argument applied, and then you do the next one, the next one. Yeah, it's a freebie. Like referential transparency. And that just means that when I was showing you earlier that these expressions, triple equal sign, or this name, triple equal sign, this expression, that those are completely identical, right? And you can do equational reasoning with these things. And trust that it's always going to work, because there's no such thing as global state when you're writing stuff down on a piece of paper. Like, where's the global state? There's no memory. This is not a Turing machine. It's just symbolic manipulation. OK, so I told you I cheated a little bit with this example. Here's what the real thing looks like if you're working with just lambdas. Can you even read this? Well, you couldn't. If I blew it up, you can't read it anyway. So this is the whole thing. And if you sat down and you worked this out with a pen and a piece of paper, like I did, so that in the event that someone was in the audience and did this and found that I was wrong, I wouldn't be embarrassed. It works. These are the reduction steps for this is just factorial of 2. If you did factorial of a higher number, you get to the point where it will take you until the heat death of the universe to compute, probably. But you can see how the reduction steps ultimately get you to the same answer. There it is. Lambda f dot lambda x dot f of x is 2. So now you know the factorial of 2 is 2. That is the entirety of the syntax of lambda calculus I want to talk about. Are there any questions? That's like more than I wanted to do, in fact.
You mentioned a lot of paper and pen. When you're learning lambda calculus, do you recommend to use paper and pen or use
Yeah.
Yeah.
No, paper and pen. It's easier.
How do you check yourself because there's no compiler when you write it?
It's a good question. How do you check yourself?
Yeah.
I just did.
Okay.
This is a proof, right? It works.
Well, another one is like if
You can do it. You can do it and make sure I did it right.
in lambda calculus, you know what 3 plus 0 is in real life.
Yeah.
So you like that's you don't get 3 plus 0 in lambda calculus.
Right.
You know you did it wrong.
Right. Yeah. I mean, this is just I'm establishing a principle essentially. Yeah.
So basically, the y combinator enables a function to call itself successfully right up to the point where it reaches the base case.
Yes. If you have a base case.
That means
If you don't, then it diverges forever. It never converges on an answer.
similar to the for loop or an iterator in the programming language.
Similar to what?
Like a for loop, like a loop. in an iterative language.
I don't love comparisons to imperative programming constructs. This is what it is. Yeah. This predates for loops, I think. Pretty sure. All right, enough lambda calculus. Now we're going to do JavaScript. Thank God, right? Something everybody is familiar with. So I hope that everybody... Can everyone see that? Is that big enough? No, not. OK. Maybe... Oops. Oh, great. How about that? Or that? Is that good?
It might help with either a dark background or knock some lights.
Yeah, my normal background is even lower contrast. I thought maybe this would be easier. No, not so much? I can do dark back.
The source file is different.
This is slightly different, but it's almost exactly identical. Let me see. Why am I using BB edit? Do you like this better? Yeah, okay.
Need a designer. I think even just like optimal contrast.
Hi. Bigger? Whatever, I don't care. So at this point, I hope you can all open up the file and open up your Java. So if you, I don't know, I'm doing this in Chrome, and I tested it in Safari and Firefox. I don't know off the top of my head how you open a JavaScript console in Safari or Firefox. Command Option J in Chrome if you have the lambda.html page open.
I think it's Control-Shift-I.
Sorry, question? Okay, so now we're going to move more into like more of a workshop format because that was a little bit more explanation than I had wanted to do. You have all of the functions that I've shown you and a lot of other stuff. And what I want you to be able to do with now is like really play with them in your browsers. The point is, I don't want to like lecture at you. Here's what functional programming is all about. I actually want you to use these functions and build computations with them so you learn not only what functional programming is, you develop this intuition that will allow you to explain it to others, right? This sense, like, what does it mean when we say functions are values? That is the whole point of what I did this for. So type stuff in as I go through these things. And I'm just going to go through the code, essentially. And I just want you to play with it in your browsers, see what you can come up with. There are a couple little exercises that you can do if you want. I actually have never given these kinds of exercises for a group before, so I don't know how that will go over. So we'll just find out. So now we're in JavaScript. Maybe you'll see the magic for real. We're only going to use the anonymous arrow function to do everything. So starting with operations, this is what I showed you, alpha, beta, and eta conversion. If you type these in, these are like our little sort of toy proofs. They work. There's true. I should note also, this file has a bunch of helper functions because we need to translate between JavaScript and lambdas. Otherwise, we can't read anything. Like for example, I can type in 1, but it looks like that, which is like lambda f, lambda x, f of x. We know that that's 1, but good point. How about that? Yeah. OK. So here's our identity combinator, right? ID equals x, returning x. Assuming everybody is either familiar with the JavaScript arrow syntax, or this is trivial enough that you can pick it up. Here's our true and false. We already saw that. A function that takes two values, x and y, and returns x is true, and the opposite is false. And again, you can cut and paste these things to test them. I have a toBool function that you can and true, false, returns false. So they work, thankfully. At some point, you will probably be able to break this because JavaScript isn't designed for deeply nested function calls. So I wouldn't try calculating the factorial of like 10. So here we have and, we have or, we have not. And play with this stuff. Type it in, see what you can do. Just become comfortable with it. That's kind of all I want you to do right now. And true returns true, right? And false, false returns false. Well, actually, this probably won't work because these are just functions. Oh, and look, it works. How about that?
I'm having confusion with the arithmetic operator. If I type in plus,
Yeah.
any plus expression, it looks the same, but then the two ends work instead of right down.
What do you mean?
It typed 1 plus 1 5.
Oh, you did like that?
No, with the constant, with the name constants.
You did this? 1 5?
Correct. Change the second number to 3 or something. It's going to look the same.
Oh, that's
But,
yeah. That's
but your two end function does work as expected.
yeah. I don't know why it does that. That's just the way the Chrome console works.
It's just a function.
Yeah. Chrome's like, what are you doing?
No, but
Yeah, so we have to. You can look at the utility functions. They're at the bottom of the file.
okay.
Just for convenience, I'm converting back and forth between these lambda expressions and primitive values. Okay, so little exercise. Try to implement XOR. Right? I've given you and or not. See if you can come up with XOR and what that would look like. And when someone comes up with it, raise your hand. We don't need to take all day. Anyone have a good XOR implementation? Right, this is exclusive OR.
Is it two ands or together? Or is it something smaller?
It's not. No, I'm not trying to trick you.
Okay, so I mean, I haven't written it formally yet, but it's basically A and not B, or not A and B.
I think that's what I got. Right? You can test it. I don't know if I've actually typed this in XOR. Yeah. So, yeah, I haven't actually typed it in yet. So. Yeah, and I encourage you to test these things too. Prove it to yourself, right? Don't believe me. Or find mistakes. There are a couple little weird bugs. Well, there's one that I can think of that you probably won't encounter. By and large, this works about 99%, which is pretty good for JavaScript, right? Here's branching. Remember before I said that in principle, the if-then-else statement you can write is this function that takes it takes a predicate, right? A function that returns true or false, and then two values, x or y. And if p is true, it returns x. If it's false, it returns y. And as we did with lambda calculus, you can do this in JavaScript. You can factor out the x, factor out the y, factor out the p, and it's just the same function as id. And now you can write, I don't know, if then else. So if this is true, return true. If not, return. Maybe that'll work. Yeah, that works. Here are the natural numbers. Here's some enumeration functions. I can explain a little bit how predecessor works. It essentially will take a pair of values, a pair of zeros, and it will increment one of them up to the point. So if you give it, let's say, predecessor of 5, it'll increment one of those values to 5, and it will increment the other one. It will like skip one of the increments. It will skip one of the increments, right? So then you get 5 and 4, and then just it selects for the 4. That's something I could probably demonstrate at great length, but it would take too long, and so I won't. But I do have a reduction to show you on that. And because this talk is, for people who don't want to learn lambda calculus, I don't care if you learn lambda calculus. I just want you to get comfortable working with functions so that you can understand their expressive power and why we do functional programming. We're building actually an entire programming language within your JavaScript console right now. I don't know if that's apparent. Like you can start putting more complicated things together with these primitives, and ultimately, in principle, you can do anything. I'm not saying that you should write programs out of these lambdas. This is more of a, I'm really nervous right now because John said earlier at the end of the keynote that these workshops are meant to be teaching skills. I'm not sure I'm doing that, yeah.
Thank you for being patient with my question.
No, yeah.
I would like to know with and, when I'm passing in true and true, in your example on line 46, what that evaluation looks like. I would imagine the true goes into the x,
Yeah,
the true goes into the y,
yeah.
and then in the body, I'm not clear on how that evaluates the true. Does that make sense? I kind of want to see the beta reduction.
Yeah, I'll try. Let's see. Let's say we'll say a equals. So let's say, I can apply true to the and function,
Right.
and I'll just get another function back.
So the x in that case,
Yeah,
and what happened to it?
it's in there. It's I closed over it.
I would think that the x would be true now.
It is, but I haven't like evaluated the function. I haven't reduced if I two-booled my little a function, it gives me doesn't know what I'm trying to do. No meaning. So I've actually partially applied the true to my and. So now I can apply the false. Let's say b is a applied to false. Now b is fully applied. Now I can two-bool on the b. Is that meaningful as far as reduction steps are concerned?
I'm just trying to understand in the scale how that.
Let's see. Okay. No problem. You're making me think on my feet. That's good. I can just type it in, right? It's just a function after all. It's not special. So this is and, right? So I want to apply, in fact, I'll even replace the false with,
Even two truths is fine, whatever works.
well, I don't know. I've not done this before, so why not do it the hard way? That's my motto in life. Okay, so I'm actually going to get rid of the two-bool because it's going to confuse me for a moment. I think that looks right. I think that's the and function. Right? So now I can apply like a true to it, for example. But instead of applying the true, let's just kill off the x and put it in there. All right, let me start over because I'm going to confuse myself. This is good. I'm glad we're doing this because this is the point.
I don't think else is simply
No, this is good.
I don't care. It's helpful for me. This is about, look, this talks about me. It's not about you. Okay. I actually might leave the false in as it is, because you get the idea, and I don't want to waste time being confused. Okay, so there's the true. We're going to apply this to true. But instead of doing that, we'll kill off that x, and we'll just stick it there, right? I need some other Boolean value, right? Because I need, we need 2 branches. So let's say the other branch is false. Right, so now I kill off the y, and now I have false.
So what, that's hard to understand.
Okay, but remember, true is also just a function. It's a function x, y, that returns x.
Oh, okay.
Right, so then we have this false. We take that and kill off this x, and then it's there.
Okay.
Then we have another false, and we apply that to y, and then we're left with false.
That last little bit there, when you said you applied it to y and you ended up with false. That was just 2 falses? Is that why? Or can you just
You know, it's tricky because I'm just branching using Booleans. I'm not branching using real expressions. Maybe if I say, is 0, 1 true, otherwise false, something like that.
That was helpful though, how you reminded me that true was a function and then that substitution, that was the bit I was missing. So.
Yeah. Remember, everything is a function.
Yeah.
They tell you this in FP, but you don't really know what it means. Then you just walk around going, everything is a function. Functional programming is programming with functions. No, it's not intuitive at all. I don't think it's intuitive. But once it becomes intuitive, it's awesome, right? Like,
That 1 is a function.
1 is a function. Yeah. Right,
You
no.
understand addition is a function.
You think I'm trying to trick you, right? Programming, I must have embedded primitive values into this somewhere, right? I have not. They're all just functions. They're simply encoding what, like, I'm a human being. I'm going to say this is true. The computer or the notation doesn't know what true means.
They all evaluate to the ID.
You know what? True and false are really bad names. Names are hard, right? This is not philosophy. It's just computation. So I'm just trying to make decisions.
Yeah.
Like, is 0 false? Why? No, really, I want to know. Does JavaScript think 0 is false? I don't even remember.
The string 0.
Oh, that's reassuring. It's not reassuring that that's not a type error. I mean, it should return like something like that probably. Anyway. Oh, what does double equals do? Oh man.